So let me ask what the parameter I applied is. 30, good. Let's check the phi parameter. Let's make this 0.66667. New null clines. Okay, we're good. Let's look at the direction field, but I just want the direction field. That's what I was looking for. So notice that at the extremes of the field, the arrows are at like 45-degree angles, especially in the high voltage area. So now let's change the kinetics. So parameter phi, and I'm going to change it to 0.26. Null clines are the same. So the null clines haven't changed. Now let's look at the field. And we'll do direct field 16. Can you see how they're straighter on the up and down? Because the kinetics are faster. So now let's look at what the stable and unstable manifolds look like. So singular points mouse. I'll click on this guess. Print the eigenvalues, yes. Draw the invariant sets, yes. So there's 1, 2, 3, and it doesn't go all the way in because I didn't run it long enough, but this point would have connected directly to that spiral point in the middle. And the outgoing unstable manifold connects back down with the stable equilibrium point. So now if I close this and I'll do numerics total, if instead of 120, if I do 200, that should be enough to show all the points. So I'll change the parameter phi back to its previous value. And now do singular point mouse. Print the eigenvalues, yes, invariant sets. And now you have that heteroclinic orbit going all the way back around. So you can see how the phase plane is qualitatively similar. So now what I really want to show you is how we go past the show into the saddle node bifurcation. So I'm going to go back to the parameter phi, make it 0.23 again, which is what I was really interested in. Draw the null clines. And now let's change the applied current. So now let's go up to from 30 to 35. When I do that, if I draw the new null clines, see how the red curve shifted up? So we're coming up closer to the saddle node bifurcation, but we're not there yet. We still have both the saddle and the node. Now let's take a look at that singular point again. See how close those two are? We've actually passed this. We've actually passed the show bifurcation. We're a little bit past it now. Let me back up a little bit. I want to get a little bit closer on the other side of it. Make the applied parameter IO. Let's make it 33.5. Okay, now we're really, really close. So again, what I'm trying to show you here is the outgoing unstable manifold connects back down to the stable equilibrium point. We're still below the show bifurcation, and that unstable equilibrium is still making a connection to the saddle. That blue curve is growing, and then the kind of mustard yellow curve is shrinking, and then when we pass the bifurcation, they annihilate one another. So let's go past the bifurcation again. So I'm going to go parameter IO, and let's go, I think it was 35, 36, I was past it. So now we're past the show. Draw the null clines. We have not hit the saddle node. We still have both points, but we've passed the show. So now the orbits have switched positions. So see, the mustard yellow curve has curled right back onto itself and created that limit cycle. So the orbits have switched positions, so we're past the show. But we haven't come to the saddle node yet. So we can keep going. Let's keep going. Let's say parameter IO. Let's make it 40.5. Hard to tell if we've passed it yet. It looks real close. I think we have passed it. So what will we do if we have a system here? If we've passed the saddle node bifurcation, then we no longer have a steady state here. So we should have a global attractor, not global, but we should have a limit cycle attractor out there. So let's see if we do. So I'll go to initial conditions, mice, which will allow me to just drop many initial conditions. So I'll put one out here. I need to go longer. Continue. Continue until 2000. See? Found it. Found it. Found the limit cycle. Did you notice how slow it went right over here? The ghost of the saddle. The bottleneck. Those two null clines are very, very close together, so it took a long time to get through it, but it eventually found that limit cycle. Okay. So let's try some other one. Initial. There's our null clines. Let's do initial mice. Put one out here. Finds the limit cycle. That goes through that point and finds the limit cycle. And if I put one here, it's going to go inside to find that stable equilibrium point. Because remember, in the bifurcation diagram, there was an unstable periodic orbit. This was a region where there was stable equilibrium point inside. So past the saddle node bifurcation, there is a stable limit cycle, but there is also an unstable limit cycle and a stable equilibrium point inside it. That maps directly to section 5 in your bifurcation diagram. Okay, so let's go to Berkeley now. So this is tri-stability. I introduced two current pulses, one which happens at about 245, and then another one which comes on at about 555. The first one knocks us off the limit cycle onto the stable equilibrium point. And I'm plotting this in W right now. I don't want to do that. I actually want to plot this in voltage so you can see this much better. So I go to graph, choose variables, and I actually want to make V visible, and I want to make W invisible. That's what I wanted to show you. So this is our Morris-Lee car system with type 1 parameters, but I've made phi 0.25, and I'm trying to show you tri-stability. So there's our limit cycles. At 245, a pulse turns on, knocks it down to the stable equilibrium point. At 555, I pop it again, goes back into the limit cycle, and then at 293.3 or 273.3, no, 793, I popped it again. And this is, so I figured out this one and this one in 1 minute, and then this one took me 44 more minutes. I kept getting this system that would spin like this, and I thought, oh, it's not stable yet. It's not stable yet. However, remember how my phase plane looked, how windy that orbit was? It's really, really, really spinny. So if I run this for a lot longer, it eventually does settle down. So here's that simulation. So it will eventually settle down there after my third pulse. And you'll notice in my sidebar right here, I have 3 different pulses. I have amp 1, amp 2, and amp 3. T0, T1, T2, T3, T4, T5. This is just using my step functions. Step it up, step it down, step it up, step it down, step it up, step it down. And I'm using different amplitudes each time. So let's see what else we got. It's about 3:15. I got 5 more minutes. Everyone good with this model? This is just showing you tri-stability. This is not bursting. This is just me giving step commands. I want to show you bursting, so I see a few of you scrambling to copy things down. I don't want to stop you if you're still copying something down. Can I move on? I see you frowning. Come to me right after class if you didn't get something, all right? I want to be able to show the bursting model. All right, let's see if I can go back to this one. And let me... So I want to make sure this is what I think it is. So I'm going to click on my equations box when things settle down. Okay, so this is the full calcium-dependent potassium current bursting. So in my equations box, dV dt equals I applied, G leak, GK, G calcium, and then there's another equation in there which you can't see all the way to the right. I'm sorry, this one is the really simple one, because I'm only adding I at the end. And then I is given by epsilon times V minus V naught. So this is the simple one. All right, let's go. Please work. Oh, this is in the phase plane. Okay, so voltage is on the x-axis, and applied current is on the y-axis. So there's the voltage trajectory of the square wave bursting. And you can see that it begins at a saddle node. The troughs of the action potentials are always above the baseline, and then the spikes slow down at the end. And we're running out of time, so I'm not going to show you the calcium, but it looks just like the slide. The calcium will just be moving like a sawtooth up and down with this. Okay, so we'll pick this back up on Tuesday next week. Have a good one.